Let's now revisit machine learning like we studied during the listen chapter and the naive Bayes classifier as one method for machine learning. Let's try to do this a little bit formally in a manner so as to make some of the material that will come later fall naturally into the same formal framework. We have a bunch of data, in this case features x1 to xn, which are, we call x, capital X, a vector or collection of features. Earlier we had different examples, the query terms that we used, the words in a comment, and in general, anything that we observe about instances which we then want to classify into different classes. And then we have some output variables, which are the labels that we would like to assign to a class, whether a positive sentiment or a negative sentiment, or a buyer or a browser. And in this case, we'll say the output variable is 0 if it's a buyer, a 1 if it's a browser, a 0 if it's a negative, a 1 if it's positive, and so on. In general, we might have many different output variables, each of them 0, 1, and the points in the space X could be shown as points in some high dimensional space. I've shown them here as just points in a plane, but in general, each of these will have many coordinates, like n, for example. And some of them are red, that means they have a 0 assigned to them, and some of them are blue, that means they have a 1 assigned to them in terms of the y variable. And the goal of classification is to figure out, given a new point, whether it's likely to be red or blue. In general, this need not be a binary task. You may want to classify it into 3 or 4 or many classes. But for the moment, we'll stick to binary classification as it makes things a bit simpler. Now, to formally model the classification problem, if you have a bunch of features in a space, we define a function, let's say f of x, which is the expected value of the output variables y given the input variable x. Now, this is a little different from what we had earlier, which was the probability of getting some variable y equal to 0 or 1 given a particular combination of x's. But as we shall soon see, it really is the same thing, at least for classification. But for other types of machine learning, we'll have different values of f, and that's why this framework is useful, so that it unifies our whole concept of machine learning. So what we're trying to do is figure out what is the expected value of y. Is it a 0 or a 1? Is it closer to 0 or closer to 1 given a particular combination x? Well, the expected value is nothing but, and clearly y is 0 or 1, then the expected value is 1 times the probability of y equal to 1 given x plus 0 times the probability that y equal to 0 given x. Now, since you multiply by 0, this term disappears, and we simply get the probability that y equal to 1 given x. And this is exactly what we had earlier estimated using various assumptions like independence and the Bayes rule. And we could figure out that then all we needed was a training set where we could compute the required likelihoods that would enable us to compute the probability of y equal to 1 given a combination x. Now that's fairly basic, but this formulation tells us a few things. First, it's not always necessary to compute this probability y equal to 1 given x directly. We did that through some approximation in naive Bayes. we might instead want to compute this function f of x. In this case, it turns out to be just the same as this probability, but in other cases, it might not be the same. For example, if you have a classifier where you didn't have two classes, you might have a different combination of f. The second thing it tells you is that the probability is one way of figuring out where a particular combination x belongs. Another way might be to somehow estimate this f and estimate the boundary where f of x is more than or less than a half. For example, in this case, if you could figure out that the boundary lay somewhere along this line over here, so that we minimize the number of false positives and true negatives, we could find a much easier way to classify the points as being positive or negative than actually computing this rather complex animal, which is the a posteriori probability. Directly trying to find estimates of f is what more sophisticated machine learning techniques like support vector machines end up doing. They do other complicated things like changing the nature of the space. So instead of dealing with the space as it's given, they use various combinations of the x's, sometimes squaring them, sometimes doing other funny things to them to project this space to a different space, and then find a line or a plane which nicely separates the instances of positive and negative. So what they're really doing is trying to estimate the function boundary f directly without actually computing the function directly. Now, that's a rather long-winded way of defining machine learning, but it will serve to unify the different types of learning that we'll see as we go along this week. Let's take a look at some examples using this new notation that we just introduced. Recall our machine learning of whether somebody is a buyer or a browser based on the queries that they issue in a search box. In this case, the queries that we had last time were red, flower, gift, or cheap, and we had various instances of people querying and then possibly buying or not buying. So our x was essentially the set of query words, the y was whether or not one buys, and so we have y comma x as our space, b, r, f, g, and c in the notation we had last time. Similarly, we had machine learning of positive or negative comments. In this case, the sentiment was the y. The set of all words formed our x, which is an extremely high-dimensional space. A word could either be present or absent in a comment, and all of these were still binary variables. We'll turn to another example now. Imagine a baby observing various animals and wants to figure out which animal is of what name. So we have various features: the size of the animal, the size of the head, the noise the animal makes, the number of legs it has, and the animal itself. And the baby observes many instances and somehow is able to discern these features in terms of whether or not the size of the head is large or small or medium, or whether the animal itself is large or small, and the noise that the animal makes, etc. The machine learning task is then to classify a new animal into the appropriate category: lion, cat, elephant, etc. So here y comma x is now the animal itself is y, the size of the animal, its head size, its noise, number of legs are the features. It's a fixed set, say here only 4 features, of multi-valued categorical variables. So they take values in specific categories. They're not real numbers, for example. They take one of a few categories, small, medium, large, for example. And lastly, we consider another example where we have customers going to supermarkets and buying bunches of products together in transactions. A transaction might consist of milk, diapers, and some cola. Another one might consist of some diapers and beer. Yet more transactions will have different products. And here we have, interestingly, no output variable, but only features, which are just the items that people buy. And the items are, again, multi-valued categorical variables, but they're a variable set, just like the comments that we had earlier, that you could consider the set of all possible items and have binary variables, or you could have a variable number of features and multi-valued categorical variables. These examples are all cases where one could do various kinds of machine learning. In the first 3 examples, that is queries, comments, and animals, there was a clear output variable which indicated the class of the particular instance. And so one could imagine a supervised machine learning scenario using something like a naive Bayes classifier to compute the likelihoods and estimate the a posteriori probability, or as we have just seen, the expected value of the class given x. In the last example, transactions, there was no output variable, so the task there is a little bit different, which we shall come to very soon. Do go back over the formalism and make sure that you're able to figure out how classification happens in each of these cases. That is, exactly how the y and the x are formulated so that we get a formal representation of the problem in terms of features and an output variable. In this particular case, of course, there is no output variable, as we have already mentioned. And let's now get into the reason why we had that.